Hello everyone, my name is Ewelina Pawelczyk. I'm a graduate with a master's degree in chemical technology from the Gdańsk University of Technology in Poland, and today I'm going to talk about advanced oxidation processes combined with cavitation for wastewater treatment. To start with, advanced oxidation processes are technologies based on the generation of highly reactive radicals such as hydroxyl radical and sulfate radical, and owing to their high oxidation potential, they can oxidize even highly persistent organic pollutants, leading to complete demineralization. So AOPs are promising alternative techniques to biological methods in wastewater treatment. Among others, AOPs include oxidation reactions with the use of lead, hydrogen peroxide, persulfates, or ozonation. A recent trend in treatment of industrial effluents involves the use of AOPs combined with cavitation. And cavitation can be described as physical phenomenon involving the formation, growth, and collapse of cavitation bubbles in a liquid medium. The methods most commonly used for the treatment of aqueous effluents include cavitation affected by ultrasound, so-called acoustic cavitation, and hydrodynamic cavitation resulting from fluid flow in a constricted section of a pipe, for example, Venturi tube, as shown in the picture. And decrease in a local static pressure in a stream of flowing liquid results in a drop of its boiling point, which causes increased evaporation and the appearance of gas bubbles. And during a subsequent increase in pressure, the bubbles implode, resulting in regions with extreme conditions exceeding 4,700 degrees Celsius and 9,800 atmospheres, which are sufficient to cause thermal decomposition of organic contaminants and dissociation of water molecules to yield hydroxyl radicals, reacting with the target contaminants present in liquid phase. Recent studies performed in the field of AOPs highlight a high synergism in case of their combination with cavitation phenomenon, resulting in increased effectiveness of degradation of even highly refractory pollutants. Researchers emphasized complexity of the impact of various parameters of the effectiveness of the pollution degradation, among others process parameters, concentration and kind of contaminants, kind of cavitation devices, amount and kind of external oxidants, and presence of catalysts or inhibitors were investigated. According to literature reports, the effects of temperature on the degradation rate depends on two opposing phenomena. Firstly, an increase in temperature results in decrease in cavitation rates due to excessive generation of cavitation bubbles and consequently lower energy of their collapse. On the other hand, an increase in temperature favorably affects the kinetics of reaction of oxidation by increasing the rate of reaction. Furthermore, the contaminants can get inside the cavities due to increased volatility and degrade during the collapse of the gas bubbles. As a result of these opposing effects, it is essential to optimize temperature for specific contaminants and treatment. The cost to benefit analysis is important for the treatment to make sure that the increase in extent of degradation at a higher temperature is not outweighed by the cost of heating of treated medium. The table presented in the slide summarizes reports of researchers regarding various effects of the impact of temperature on processes of degradation of pollutants. An example of this effect was provided by the investigation of Wu et al., who observed a decrease in the extent of degradation of chlorocarbons with an increase in temperature of the treated medium when using hydrodynamic cavitation alone. The authors attributed this effect to formation of an excessive number of the cavities, which suppressed degradation by decreasing collapse of the individual cavities. On the other hand, in the case of the degradation of rhodamine B, the reaction rate increased as temperature increased from 30 to 50 degrees Celsius. However, less degradation ratio was observed at temperature 60 degrees due to higher impact of the attenuating effect than the kinetic effect. When cavitation is combined with Fenton reagent, the kinetics of oxidation plays a more important role than the number of cavitational events. Thus, a higher temperature significantly improves the rate of the degradation process. The positive effect of higher temperature was also demonstrated in the case of hybrid oxidation processes combining hydrodynamic cavitation with persulfates. Due to the activation of persulfates, hence a larger number of generated sulfate radicals, resulting in increase of the reaction rate. Considering pH, to a large extent the optimal value depends on the nature of pollutants, and most often it is selected by experiment. However, degradation of organic pollutants is most often carried out in an acidic medium. According to the literature, acidic conditions were found to promote more efficient generation of hydroxyl radicals, mostly through intensified dissociation of an oxidant and autoprotolysis of water. Furthermore, the oxidation capacity of hydroxyl radicals is higher under acidic condition. This can be attributed to a lower rate of recombination reaction of hydroxyl radicals, which is only possible under acidic conditions. For hydrodynamic cavitation combined with persulfates, acidic conditions are preferred due to a lower amount of sulfate radicals is transformed to hydroxyl radicals at a lower pH. In case of the lack of possibility of pH adjustment, for example, in the risk of contaminants being released to the atmosphere within effluent acidification, hybrid process can be carried out at a basic pH. An interesting example of such a case is the effective degradation of sulfite ions and organic sulfides present in strongly caustic effluents from the production of bitumens by use of cavitation-based IOPs, because the adjustment of the initial pH from strongly basic to acidic in this case would result in the emission of hydrogenous sulfide. Gongol et al. Emphasized that the kind of acid used to acidification strongly affects the effectiveness of radical processes of oxidation of organic contaminants, as well as formation of harmful secondary pollutants. They investigated specific effects of free inorganic acids on the degradation effectiveness of organic pollutants in hydrodynamic cavitation-based AOPs. The contaminants included 20 organic compounds containing oxygen, sulfur, and nitrogen atoms, which are most commonly determined in industrial effluents. The obtained results reveal that the presence of chloride ions precludes effective oxidation of the target organic contaminants. This can be attributed to scavenging of hydroxyl radicals in so-called chlorine pathway, which results in formation of species with a lower oxidation potential. And furthermore, side reactions lead to formation of secondary pollutants. Nitrate ions are characterized by strong oxidation properties without hydroxyl radical scavenging effect. in the presence of refractory organic contaminants such as heterocyclic compounds, nitrate ions facilitate their conversion into salts with easier degradability. However, a side effect is the generation of secondary pollutants. In case of sulfuric acid under cavitation conditions, sulfate ions are converted into sulfate radicals, having remarkable oxidation potential, and moreover, sulfate radicals have a longer activity period than hydroxyl radicals, which allows a longer exposure of refractory contaminants to their attacks and thus an increase in the effectiveness of degradation. Sulfuric acid was the only chemical used for acidification, in case of which monitored type of secondary pollutants were not formed. Furthermore, the best treatment effectiveness was obtained in this case, in most cases much above 80%, along with 90% total organic carbon removal. Reagents used for the chemical generation of hydroxyl radicals, among others, include hydrogen peroxide, ozone, persulfate, and peroxymonosulfate. The oxidant should be selected experimentally, depending on the type of effluent. To a large extent, the efficiency of this process depends on the amount of added oxidant. Insufficient amount lowers the efficiency of degradation due to insufficient amount of generated reactive radicals participating in the degradation reactions. On the other hand, excessive amount lowers the efficiency, mostly due to the formation of radicals with a lower oxidation potential as a result of secondary reactions. Furthermore, under industrial conditions, an increase in the amount of oxidant during treatment of millions cubic meters of effluents causes very high production costs. The feeding mode of an oxidant to the reaction system is also important. Addition of a specific amount of oxidant can be done stepwise, which often improves the efficiency of treatment, or as exemplified by the study of Zhang et al., in which the stepwise addition of oxidant was found to improve the efficiency of pollutant removal by 16% compared to the single-step addition. It can be attributed to the fact that stepwise dosage of an oxidant prevents sudden increases in concentration of oxidant, which promote depletion reactions. Sodium persulfate recently attracted the attention as a promising source of sulfate radicals due to its moderate cost, high stability, and aqueous solubility, and the combination of high oxidation potential of sulfate radicals and longer lifetime than commonly used hydroxyl radicals makes it very effective for the degradation of refractory organic compounds. However, the production of sulfate radicals is impeded by the symmetric structure of persulfate anion and relative high bonding energy between oxygen atoms in persulfates, and the energy released during cavitation phenomenon can be utilized to break this bond and to convert persulfate into sulfate radicals. Researchers have reported a lot of the benefits of the hydrodynamic cavitation combined with persulfate system. For instance, formation of both sulfate radicals and hydroxyl radicals was beneficial in degradation of bisphenol A due to attack of hydroxyl radicals on the aromatic ring at ortho and para positions, while sulfate radicals participated in sequential ring opening reactions via hydroxylation, which resulted in high synergistic effect. This hybrid system is also advantageous in the benzene, toluene, ethylbenzene, and orthoxylene degradation process, which was examined by Fedorov et al. And resulted in enhanced degradation efficiency. Activation of persulfates is also possible by using carbon-based materials as catalysts. These materials include modification of carbon, such as activated carbon, graphene oxide, nanodiamond, carbon nanotubes, and graphite. An interesting group of compounds that could be an alternative to currently studied materials are asphaltenes. Advantageous properties such as high thermal stability, low production cost, and extensive availability make asphaltenes as an appealing carbonaceous material for heterogeneous catalysis. Recently, the first attempt on using asphaltenes for activation of persulfates and peroxymonosulfates under ultrasound irradiation was reported by Fedorov et al. In terms of activation of persulfates, the particles of asphaltenes intensified formation of reactive radicals by creating additional centers of cavitational events. Moreover, owing to pi-pi stacking interaction between asphaltenes and sp2 hybridized systems of BTEX, the contaminants undergo adsorption on the surface of asphaltenes and subsequent oxidation by free radicals. In order to evaluate the catalytic activity of asphaltenes on BTEX degradation in ultrasound-assisted persulfates and peroxymonosulfate systems, a series of comparative experiments were conducted. As shown in the table, degradation efficiencies were considerably increased for both ultrasound-assisted systems in presence of asphaltenes, indicating their potential use in catalytic degradation of BTEX. For instance, in case of persulfates under ultrasound irradiation system, the degradation of BTEX significantly increased in presence of asphaltenes, and also a high synergistic effect was determined. The authors gratefully acknowledge financial support from the National Science Center. Thank you so much for your attention.